Yeah, so I'll just formally introduce that. Yeah, this I'm Krishna Sen Avatar, a PhD scholar, just in my fourth year. So this lecture series will be a part of ISSS PMRF course on Introduction to Differential Geometry. So as per the plan, we'll have around 24 hours of lectures, and the idea is to cover all aspects, so to speak, from an engineering point of view. What all the concepts which are required to say study differential geometry, as well as to use it in our own research. So that is the goal eventually. So I would like to request every one of you, just could you please give give me a slight introduction, like give us a slight introduction about yourself.
Hello,
Yeah,
hello,
hello,
hello, Krishna.
hello.
This is Teja from Web Technologies.
Yeah. So may I know, I mean, what are your interests and what is your educational background and all?
So basically, with a BTech background, we are from Web Technologies. It's a company. So we do this modeling and all. So just want to learn these advanced techniques, like in surface modeling and all.
I see, I see, I see.
I
Okay.
heard this VM technologies long back, like while I was in 2014. So they few people who did masters from aerospace engineering at IIT Kanpur, all
Yeah,
that batch, all those people they were recruited in VM and VEM. One of my
yes,
BTech seniors, who is from IAR, Institute of Aeronautical Engineering, he was also there. If I'm not wrong, this is from Hyderabad, right?
yeah, Hyderabad.
I don't know
Yeah,
what
you are
he's doing
talking
there.
about the same company.
Yeah.
Uh,
So, do you know Manikanta? His name is Manikanta. He's maybe super, like it's almost 10 years. I'm not sure if he's still in the same company there.
I joined recently here. Mm,
Okay. So, you done your masters or just did your bachelor's?
Graduate,
Graduate
undergraduate,
is like
UG.
UG, undergraduate. Okay, cool. Okay, I will introduce myself. I am Dinesh. I am currently postdoctoral at IIT Delhi, working in mechanical engineering. Currently, I'm looking at batteries, modeling batteries, but I work with mathematical modeling using meshless techniques, especially handled fluid mechanics problems and solid mechanics problems. I had a little bit of inclination towards mathematics, abstract mathematics, and of course, learning differential geometry will open doors for a lot of other stuff to learn. I've been tried a lot, but it was a failure. I hope. I mean, no one uses differential geometry as much as Krishna, so it is only helpful for him. So I'm just here to see how he is using this in it and get out of him.
Yeah,
Yeah, that's about me.
yeah. I think we have one more participant here, Udbhav.
Yes, I'm a recent master's graduate from IISc Bangalore, and I know the course instructor, and I was interested in his field of research. So thin shells, and in my undergrad, I have worked in like contact between two, I would say membranes. So contact mechanics, basically. So yeah, I was there. We also got into concepts of principal curvatures and all that. So yeah, it will be, I would say, beginning part will be a kind of refresher, but yeah, definitely the next ribbons and all, I'm hoping to have some insights into them. So yeah, that's from my side. That's my introduction. Yeah.
Yeah. So it seems majority of us we know each other, so that's how it is. Yeah. Okay. So formally, let's start. Let's begin with the course. So I mean, we'll start with what is differential geometry essentially. So that is the first goal that we. Uh, so differential geometry is a branch of applied maths, and as you recall, so applied maths. Uh, let me just okay. Yeah. So here we study fundamentally the the geometry of curves and surfaces. That is the idea. Curves and surfaces. And we use all those ideas from math, such as say multivariate calculus and of course linear algebra. Nothing works without linear algebra in applied maths. We have also tensor calculus. So from an engineering perspective, we only deal with these subjects. However, for pure maths background, we also have to use say analysis, what we call as the mathematical analysis, to say dig deeper into the field of differential geometry. Now, although it sounds to be very limited in its say in its scope, however, these curves and surfaces are very general in nature. Like they can span everything, everything that has to deal with say like whenever we have any mathematical models, right, of even if it's an abstract sense, like let me just put into perspective. Say in the field of course, the current, the very buzzword that we have is machine learning, right? So in machine learning as well, there is a lot of uses of differential geometry to understand how the so ultimately it's based on something called objective function, right? Whenever there is a optimization involved, we have an objective function, and as you recall, objective function depends on several variables, say fx1, fx2 till xn. Now, while we live in say 3D space, this when we talk about an objective function, it can be a function of n variables, and n can be as large as billions, even trillions. So just mind that it will be a surface in such n-dimensional frame, in that n-dimensional space. So it will be something which maps from Rn to R. So if we want, if the goal is to determine the minima of that function, and which essentially we look at, say it will be some minima, right? Some minima of this function. So say something lying just at the right at the well. So this is what we are looking at. In order to approach this minimum, we'll have to differentiate along these surfaces to be able to reach that point. So now you see where, I mean, interestingly, it's even used in things which are very abstract in nature. So that is, I mean, just to introduce about machine learning. Apart from this, it's widely used in mechanics, although in a smaller subset of mechanics, that what we call as nonlinear mechanics. So differential geometry is used in nonlinear mechanics, say to develop new techniques, to develop new models, new mathematical models of some structures, say for example slender structures. Apart from that, it's also used in developing algorithms, say such as continuation techniques in nonlinear mechanics. So that is one use in mechanics, one example of usage in mechanics. In physics, of course, differential geometry forms a major part of what we call as the general relativity. So I don't have much background, so I'll just say that it's like used to say perform operations on all that what we have, what we call as the space time and all dependence. So when we work in such n-dimensional spaces, when we perform calculus on those surfaces, which may or may not be imaginary, but there is where we use uh, differential geometry, apart including the field of topology as well. And in engineering, say it's also used in say electronics and communication engineering. Electronics and communication engineering to study the flow of electromagnetic waves. So yeah, so these are some of the applications of differential geometry. That was just a very vague, but yeah, some basic introduction to it. Now, what to expect from this course? Like, so first of all, the aim obviously remains that it's to introduce some of the fundamentals of differential geometry. However, there are certain caveats here that I would like not to make this course mathematically very rigorous, because that's how I have learned. And I believe that differential geometry is essentially understood more from the perspective of, uh, say, development of intuition to solve problems rather than doing just dry proofs. So that's the thing that, yeah, I would try to avoid as much as possible long and cumbersome mathematical proofs, which we may, if possible, try to introduce in a follow-up course to this introductory one. And essentially, the goal of this course is more towards understanding and eventually understanding structural models in nonlinear mechanics, such as rods, ribbons, plates, and cells. So this is something which we'll eventually look at, and we'll try as best to cover all aspects of differential geometry before we spend a good amount of time on the applications part of differential geometry. So yeah, so what do we plan to discuss here? So first of all, the entire course, I have tried to frame it in terms of 5 modules. So the module 1 is curves and surfaces. I think before this, I should just introduce which all books I'm going to follow. So which all books will be followed in this course. And yeah, I think I missed one point here, that that we would also use softwares, some mathematical software such as, of course, Mathematica. Like Mathematica. Till the point we are able to do the analytical part. And then we would also try, if possible, to say do some numerical studies using MATLAB, at the very least MATLAB or Python. But we will try as best to use Mathematica so that we gain some intuition about the ideas such as how do we define a curve and all that. Right? Now coming back, as what all books we are going to follow, right? So the main book, that's how I would like to call it, the main book that we are going to religiously follow is the book by Andrew Presley. So it's called as, the book name is Elementary Differential Geometry, and it's authored by Andrew Presley. And I'm calling it the main book just by the due to the fact that there are several number of books on differential geometry, each written in its own style with its own flavor. And the problem comes is like it becomes very difficult to merge, say, combine ideas uh, in a very, say, cohesive manner from more than more than one, say, two or more books. So we eventually would require certain, um, say, at least some unifying factor or maybe some guide which will help us to proceed along, right? So this elementary differential geometry is more like a guide which we'll be using. And about this, we will be following 2 other books. So one book is what we call what's named as differential geometry, of curves and surfaces. And it is authored by Thomas F. Bankoff and Stephen Lovett. And the other book that will partially try to use is it's called as the Modern Differential Geometry. Of curves and surfaces. And of course, using Mathematica. So I'll be using the 2000, I believe 2006 version of this book since I'm unable to get the latest copy. So the MATLAB, some of the MATLAB codes are archaic. Mathematica codes are archaic. That it's no, I mean, some of the syntax are no longer being followed. So yeah, we'll have to make adjustments as per the latest versions of Mathematica. And this book is authored by a team of by 3 people: Alfred Gray, Elsa Abena, and Simon Solomon. So these are the 3 books. We'll with all this, the other 2 books will just revolve around the elementary differential geometry books. So it's like all the topics will be sequentially followed from will be follow from this book called Elementary Geometry, and then we'll pick the relevant parts from these other 2 books accordingly, and that will, so in a way it helps us to gain more ideas about some topics from all these 3 books, but keeping this as the main lighthouse, so to speak, right? So now we come to what all topics we are planning to cover in this book, in this course here. So at first, module 1 will talk about curves, and we'll start with definition of a curve and what we mean by arc length. We would also talk about how do we parametrize the curve in various ways. And the most famous one is, of course, what we call as the arc length parametrization itself. And then we'll talk about some curves, say closed curves. Then also about level curves. And how it is different from what we call as the parametrized curves. Then we would move on to talking about curvature. There's the most then plane curves, which are curves lying in, say, XY plane. And then we would talk about space curves, which are curves in 3D space. And we would talk about simple closed curves. Right, and some maybe try to also covers what we call as the isoperimetric inequality, if possible. Then from some other books, like the book by Bankoff, we'll try to cover, say, knots and links. We will see if we do it here, or maybe we'll do toward at the end of this course, which is in in module 5, which is advanced topics. In surfaces, the idea is that we'll start with, of course, the definition of a surface. Then what are smooth surfaces? What are smooth maps? Then tangents and derivatives. About normals, which are normal to the surfaces, and also what we call as the orientable surfaces. So orientability. And examples of surfaces such as water level surfaces, then some forms of surfaces called a general family of surfaces called quadric surfaces. Then we'll talk about some of the very important topics in surfaces such as what are ruled surfaces and surfaces of revolution. And in the meanwhile, we'll also talk about compact surfaces and introduce what we call as the inverse function theorem. An inverse function theorem is widely used in mathematical analysis, right? So the idea is like if you have some function, say f of xy is equal to c, then under certain conditions, we look at what are the conditions for which we can have a relation between y in terms of x. So it's like just slightly digression. So say we have a implicit function f of x is equal to c. Then under what conditions can we be able to have something of a function y which can be expressed solely in terms of x? So this is what inverse function actually implies. Or yeah, or sometimes I think yeah. And it also talks about the conditions for what called the invertibility of a function, right? Now we come to first fundamental form. So in first fundamental form, we look for the lengths of curves on surfaces. And as you recall, as you may say, be familiar with, when we talk about geodesic curves, right? So those are essentially curves on a surface, and we would want to know the length of, say, curves when, say, if you're moving from point A to point B on Earth, then of course it's not just the length of the a line connecting both the points, right? That won't be the actual distance. We'll have to follow the curvature of the Earth in order to reach the point. So the total distance or total length of the curve which joins both the points while still remaining on the surface of the Earth. That is what is geodesic, isn't it? So that's what we are going to look at in the first fundamental form. Then we'll talk about isometries of surfaces. So in isometries of surfaces, we talk about under what conditions can, say, the length of a curve joining two different points remain the same even when the surface is being deformed, or even if the surface is being transformed uh, by some mapping, right? So we look for those conditions such that the curves joining both any 2 points on the surface will still remain of the same length. And then we talk about conformal mappings of surfaces. And we'll also talk about what are equiareal maps and maybe slightly touch spherical geometry. Right? Now we come to the curvature of surfaces, and this is going to be the most intense part of this course. So in curvature of surfaces, we begin with the second fundamental form. So second fundamental form is where we relate, where we talk about curvatures, right? And in the first fundamental form of curves, right? So that is where the fundamental distinction between both these forms lie. So we'll start with second fundamental form and then talk about Gauss and Weingarten maps. Then we'll talk about normal and geodesic surfaces. And we'll also talk about some of the ideas which are very important in differential geometry, what we call as the parallel transport. So parallel transport, it's a connection, so to speak, where which is always torsion free, and we'll gradually learn. So it's like if we are in parallel transport, say if we are moving along one curve, even if the curve is say twisted, when we in the framework of parallel transport, we would like to have one such frame which even if it moves along the curve, it is still torsion free. So this helps us in calculating the actual torsion, right? So under what are those requirements for parallel transport? So that's what we are going to look at here, and then talk about covariant derivatives. Right? And then after that, we would move towards to discuss about Gaussian curvatures, mean curvatures, and what are the principal curvatures of a surface. And what are surfaces of constant Gaussian surface. Then of course we'll talk about flat surfaces. So beforehand, I must tell you that flat surfaces are those surfaces which have zero Gaussian curvature. So any surface which has zero Gaussian curvature, it can be developed. Again, I'm using of the word develop. Develop means that we can move. We can move from one say surface to the another without introducing any cuts and all. Say for example, you have a flat sheet of paper and you can roll it into a cylinder. That's only possible because that flat piece of paper has zero Gaussian curvature, and that makes it like you can make a cylinder. Either also we can roll it up and make it into a cone. That is just possible because it is a developable surface. And say from a flat sheet of paper, you can never construct a sphere because a sphere has zero Gaussian curvature. So if you want to, I mean, develop a sphere out of the flat sheet of paper, it has to be done, of course, very awkwardly by introducing cuts, by pasting the sides and all, right? So yeah, that's what flat surfaces are here. And we'll also talk about surfaces of mean curvature. constant mean curvature. And then Gaussian curvature of compact surfaces. Fine. And then in the advanced topics, we will touch, of course, some part of geodesics. Then our main goal is to understand what is Gauss theorema, egregium, right? And there is a very, very, it's a remarkable theorem in differential geometry. And to understand this, we would have to navigate through Gauss minority equations. And then we'll follow it up with Gauss remarkable theorem, as this theorem is called. And then we also look at surfaces of, again, surfaces of constant Gaussian curvature. Right? And this is just for the pure differential geometry part. Then we'll move on to mechanics. That is where our interests lie. And whatever is necessary to build, say, what a Rudd theory is. And of course, we'll slightly improve it to construct ribbon theories. And if possible, we'll touch shell theory. Before that, we would have to have some background here on what are, say, Christoffel symbols. And all those, we had variant derivatives. And we'll also look at other, say, other derivatives, or whatever are necessary to perform derivatives on say, on say generalized, using generalized coordinate system, right? So that is what are the topics to be discussed in this course. And mind you that we would not be over exerting ourselves by going too much into the technicalities. We would say move forward more from an operational point of view, that in every scenario we would be looking at how to use it to solve problems, and how it can, what are the operational basis for, say, if we are talking about lengths of curves and surfaces, then how do we determine the lengths of curves and surfaces? And if you are talking about all these Gaussian curvature, then how can we obtain it for any general surfaces? So our goal will be more towards understanding the applied side of all these topics. So yeah, with this, let's start our first today's session, which is supposed to be on curves, right? So we start our model 1. Yeah, before this, I hope it's not very exhausting. Yeah, hello.
Continue.
Yeah,
Keep going.
yeah. So
But don't you
we'll
think
start
it's
with,
too much for 1 month for 1 month, Krishna? That's what all I wonder.
no, the idea is like we would be, as I mentioned, right, we would be talking more about from an operational sense. Like we would not do any such theorems or proofs. We'll only look at all those topics which we can use it, and at the same time we'll also be doing a lot of mathematical work. So we
Yeah,
find some surfaces, we'll determine those values. So the idea is to approach the mechanics as, I mean, build all the necessary things in order to reach mechanics.
So here is my question.
Yeah.
Uh, but you are teaching in terms of education. I mean, instructor perspective. I get it, but see, you are going in more. I mean, I don't know what is your perspective here is, and then now.
Ha,
But
ha, ha.
to ask you, can you briefly outline us if you know? Okay, can you
Ha, ha, ha.
go down as in module 5?
Yeah.
On module 5, can you briefly outline, like maybe in couple of minutes, what a rod theorem is or what a ripple theorem? Okay, that's what I mean. This is it's not needed, but it is more your. I mean, this is how I would look at it. If you can tell us what is shell theory, like in 2 minutes, probably what all are terms there in shell theory.
Okay, just to have an overview, right?
Trying to
That's
say.
what you mean.
You said, suppose assuming if someone already explains what in navigation, like what, say, I will tell you, I'm trying to study fluid flowing inside a pipe,
Ha,
and
ha,
then
ha, ha.
I'll outline the equations. Then I will discuss what density is, what pressure is. That's what how I would
Right.
go. But because this, I'm just asking you. If it was any other course, I would have been not asked you. But this course is too intense, and I know this is like real mathematics, and it's too many terms, and it's a bit pain. We just want to know. We just want to know what we are trying to do. Like we want to know a screenplay. Like ये है. Then you can go into the scenes. Like ये है यहाँ पे comes this comes here, this comes here. If you know what exactly we're going to do, yeah. Let me just in 2-3 minutes, not more than that.
Yeah.
Yeah,
Yeah.
yeah, that's it.
Okay, so the idea is, yeah, as Dinesh has rightly put, right? So the idea is how do we use whatever we have built to say understand something in mechanics, and as people who, I think we all of us are somehow related to mechanics. So the idea is like we will build in mechanics what we call as slender structures. So the idea is that in general structures, right? Before we discuss what are slender structures, let's go a step back and talk about what are general structures. So general structures, if I call you have a block, say deformable block, it's kept on some, say, some floor, right? And it's made up of some slightly more deformable object. Say it's constructed of, say, rubber, and we are applying load over it, a distributed load. Maybe just we are pressing it with our hand, right? So of course, as we press it, it will get deformed, and what we intuitively feel is when we press it, it will bulge outwards, right? It will just bulge outwards in all sides, depending on how uniformity and how symmetrically the load is applied. So for this, when we solve such structures, we have to solve the complete governing equations for mechanics, which are rho u vector is equal to divergence of sigma plus b vector, or maybe what oftentimes you'll find people using rho b vector, right? So u here, and I'm also incorporating dynamics, taking time into account, since of course this is a time dependent problem until we settle down. Although I mean if we have spent enough time, then u double dot will be 0, so that the problem becomes a static problem. So here u double dot is what we call as the displacement function, or the, and sigma is the stress, b is the force vector, body force vector, and rho is the material density at every point. It's like a material point density, right? Which is of course only valid in mechanics, right? And only if the body is assumed to be continuum. Then in order to solve such problem, we have to actually solve the complete 3D problem, which involves solving this linear elasticity. I mean, this what we call as the Navier. This equation we call as the Navier-Lamy equations. And this is from the conservation of linear momentum, from the conservation of angular momentum. We have a direct, so to speak, the conclusion that the sigma's, the stress tensor is symmetric, right? Now, if say, I mean, of course, we have to do these simulations or do this calculation numerically, isn't it? Say we do numerical calculations, because of course for a general body it's not possible to get an analytical solution. So first of all, we have to do some discretization, which can be anything, say finite volume method, finite difference method, or finite element method, based on how the body is, right? If it's a simple shape, then we can even use finite difference method to solve the problem, right? And then we'll after discretizing, we'll have, say, n number of nodes, n nodes, and this n will be much greater than 1. So which means it will be order of some, say, 10 to the power some small n, where n could be greater than even, say, 1,000, 10,000, could go as far as even billions, depending on the, of course, the size of problem. So let's take to be order 6. So you just imagine that how much of computational effort is required to solve all this problem. Computational effort is massive. So there is where
So you just solve it in a different way, and you come to, like, you assume one dimension is less that, and you
yeah,
supervise the physics, and
exactly.
you come to it.
Yes, yeah. So from here, what we do is, of course, this is very exhaustive. So then we look at the shape of the body. We look at shape of the body, try to decipher or try to, say, understand how the dimensions of the body are stacked against one another. Right? So we look at, say, some generic length and some generic breadth or some generic height. These are all characteristic lengths. So we will just compare the orders of all these three quantities. Now, say if by chance it happens that the length is much, say, we'll do some first order approximation. I mean, say the first order of say comparison, right? Not approximation, first order of comparison. Say if the length is of the same order as breadth, say the length is 5 meters and breadth is, say, 3 meters, and height is, say, something like, I'll just call it 5 meters. This is 3 meters, and say height happens to be, say 5 centimeter. Now you can clearly see the order of difference between these quantities. So in such scenarios, we would like, and in fact it would be much more useful to solve a reduced problem, which is, of course, will not be as exact as solving the entire problem using these entire equations, but we would exploit the difference between the dimensions of these bodies in order to obtain a slightly reduced model, what we call as a reduced model. And why not just say, since h by b and h by l is much less than 1. So why don't we assume that the entire body is just some thin sheet of 0 thickness, like mathematically? So it's like we are moving from 3D body to a reduced 2D body. And then we'll solve a reduced form of equation. So we started with u double dot is equal to divergence of sigma plus rho v vector. This was, of course, easy to do, but computationally very expensive. And this one is we'll be solving some another set of equations, which is of course difficult to do, but computationally much cheaper. And this is, of course, it will be approximate. The values, the solution is going to be approximate, but that's what we need. We don't want, I mean, very accurate result. We want reasonably accurate results. So there is where the slender structures come into picture here. Now, we started with moving from 3D body to 2D body. So this 2D body is either what if it happens to be such that, so what we'll do is this body, say if it is, say, arranged or it has this morphological structure, then we'll just take a midsection. We'll just take a midsection of all the edges of all these faces, right? We'll draw a mid, so to speak, line which which just intersects, right? Divides all these edges into half, and then extract that central portion and consider it to be a flat surface with only length and breadth. So it was LBH. Now we have LNB. And if it happens to be flat in nature, we'll call it plate. And if it happens to be curved in nature, say things like sorry. So we draw a midsection, right, through all this, and we extract a curved surface from here, just the midsection. So this is what we call it as a shell. And of course, we'll have to, so you can clearly see that these are all surfaces. So we'll be using all those tools and techniques derived from differential geometry to obtain some model which explains the mechanics of this problem, right? Some model which is heavily derived, I mean, which uses tools, right, derived from differential geometry. I'll just call it DG, right? And then we solve it, and then we solve the problem, and we solve the equations and solve the model to obtain the deformation in this model. So that is one such example of slender structure, right? And based on what the length dimensions order that we are looking at, so a second class of problem is what we call as the length. So we had L, B, H. So the second class of problem is, say, what if length is much larger than breadth, and it's also much larger than height. So say L is some 5 centimeter, or say some, yeah, let's just call it say 50 centimeter. Breadth is say 5 centimeter, and height say just around say 5 mm. So we can clearly see that B by L is about 10, and H by B is again H by B is about 10. So it's like the scales vary quite a bit, although in this case it's not very significant, but that is how the scales are. So in this scenario, we would like to have a problem. So the entire 3D body, right? We started with some 3D body, and it can be modeled as a what we call as a ribbon. So L and B, and the thickness is H. So of course we are not going to use the thickness. I mean, we'll just have to incorporate in mathematically, but yeah. So that is how we have another 2D reduced model. But for ribbon, it's not exactly 2D in that sense, because we have two order of parameters here. Like we have b by l, which is of some order, and then h by b of another order. So this is sometimes referred to as 1.5D model. And the reason why is because let's move one in the so to speak the third order of comparison here. So when we have LBH such that L is much larger than B and B is of the order of H. Say in this case, say we have L to be say 50 centimeter and breadth to be something like 1 centimeter, even height to be around 1 centimeter. So such structures are called as ruts. And ruts are essentially the model what we call as the 1D model. And it's never to be confused in 1D what we literally understand 1D. It's still a 3D model. It just happens that the way of the way we formulate the problem is looks like 1D in nature, and which we'll gradually learn after we understand what are curves and all, right? So since this is a 1D model and plate is 2D model, right? It is a 2D model. I think here we have a 2D model. So ribbon, that's the reason we call ribbon as 1.5D model, although it happens to be 2D in nature, right? And so it depends on how we want to approximate the ribbon. If we use ideas from plate theory, then ribbon is a plate-like model. And if we say model the ribbon from the right side, then it looks like a 1D model, right? So that is the overarching, so to speak, the goal of what we are pursuing and what we plan to do in this set of lectures. So I think Dinesh, now things are slightly more clear, I believe.
No, I mean, okay, I mean, I get you, I get what you're doing, but the point I was trying to ask you was,
Yeah,
assuming now you write the equations of
yeah.
ribbon model,
Ha, ha, ha.
then you can say like, anyways, I mean, I mean, this is all. I mean, I'm not saying we know, but this is something. You get me right?
Yeah, yeah, yeah.
But
So
anyways,
just
yeah.
yeah, just to add, RUD is a space curve, and plates and shells are actually surfaces.
Yeah,
And
but what I'm trying to ask you is you have mentioned a lot of nomenclature in the
ha ha ha
contents.
ha.
So
Yeah,
my
yeah, yeah.
question was, where should we use those
So
terms in
yeah,
here?
okay,
You get
okay.
me?
So
So
let's
assuming now
yeah,
you have
let's yeah.
conformal mapping of surfaces.
Okay, no, let's
Okay.
start with the RUD first, I believe. Then things will become more
Anything? No, no, I'm not saying
yeah,
you should explain everything. I'm just asking you कि कहाँ कहाँ पे ये चीज आते हैं, लाइक ये जो
yeah.
टर्म्स ने मेंशन किया, जस्ट आता है, सो दैट वी नो ओके ये चीज वहां पे आ सकता है. ऐसे we like, because the terms are, or of course, we want to learn the length of the curve in rods only. We don't apply it in surfaces because you don't have curves in surfaces.
Exactly, exactly.
Mostly
Yeah,
it will go for but anyways, I get it, I get it, yeah.
yeah. So when we start with RUDs, right? So in RUDs, these are the building blocks. Uh, like what we have is so definition, arc length, parameterization, closed curves. These are just some introductory part. Curvature is of course a very fundamental to understand RUD theories. Plane curves, when we look at the planar deformation of a RUD. Space curves are what actually RUDs are, right? And these are some basic examples of what we mean by simple closed curves. What are isoperimetric inequality? And knots and links are when, say, a RUD, they intersect with, I mean, say they interact with one another. Say we have multiple RUDs interacting with one another. As an example, nodes and links are used to study when analyzing things like DNA. So as we recall, DNA consists of rod-like structures which are intertwined with one another. So to understand the behavior, I mean, to understand what are something some parameters which are invariant. So these nodes and links, they happen to be some invariant quantities when we discuss RUD structures such as of say DNA chains and all, right? So that is where we had been talking about, like this part completes what we need to understand red theories. However, when we look at plate theories or even shell-like theories, then it goes much ahead. Like we would have to discuss about surfaces, of course, definition, the smooth surfaces. What are smooth surfaces? Like smooth surfaces are those surfaces in which any operation, any calculus operations done over the surface remains smooth, or which means that they can be infinitely differentiable, right? Smooth maps are just like that, right? We are just talking between mapping from one surface to another, and those maps
Yes,
must
yeah,
also be
I
infinitely. Yeah,
understand, Krishna.
yeah,
Let's continue. Let's continue.
yeah. Yeah. I think this is a very nice question. So I'll just yeah. So tangents and derivatives, of course, these are used to build basis vectors which say cover a surface. And of course, in a surface like shell, even the basis vectors will change from point to point. So that is the reason we require tangents and normals to the surface, right? And level surface, these are some basic examples. I mean, just some examples of surfaces, what we understand, right? Say surfaces of the form of fxy is equal to constant. Then we have ruled surfaces. So ruled surfaces and surfaces of revolution, right? So ruled surfaces are used to study ribbons because ribbon happens to be a ruled surface. And then we have inverse function theorem. These just some very important tool used in say differential calculus, differential geometry, as well as in mathematical analysis, right? And when we now we move on to determining lengths of curves and surfaces on surfaces. Now this will be used to understand strains. So how do we determine strains of say a shell-like structure? Of course, we'll have to look at the lengths of the curves. How did they change during the deformation? And isometries, we look at, say, if a slender structure just deforms because of pure bending, then bending never changes lengths between any 2 points. So that's the reason, like isometry, like bending is more like uh, when we apply pure bending to a say shell, then all that we do is we are only changing the orientation of the surface. We are not extending it, because of which any curves which say traverse the surfaces, they will always maintain their initial length, right? And then equiareal maps, we have like maps which preserve area. So we choose a patch on a surface, and even after deformation, the patch still remains of the same area. So what is the requirement on the mapping which enforces the condition for being equiareal, right? And spherical geometry is of course useful to understand geodesic problems. And module 4 is where we'll spending quite a bit of time, because this is the most important part in differential geometry. The second fundamental form. Then Gauss maps are like, they are like normal maps on a surface. Then what are the different types of surfaces here, and what are parallel transport and covariant derivatives? These are again will be used to evaluate how the basis vectors change over the surfaces. And of course, Gaussian curvature is looks at something which is always intrinsic to a surface. Like no matter, even if the surface is being deformed, of course, smoothly, then there must be some parameter which still remains unchanged. So it so happens that Gaussian curvature is something which is very characteristic of that of that particular surface, which despite making any change to the surface, it will still maintain a single value or its constant value. Then we have mean surface. These are, as we'll see, that mean curvature are nothing but just the average of principal curvatures of the surface. And then we look at some example surfaces of Gaussian curvature and flat surfaces. And of course, it will eventually end up with Gauss theorem egregium, right? So we see that as we move along the courses, we are gradually moving towards understanding the mechanics of both these slender structures. So I think that is the overarching goal, yeah, just to make it clear right now. Yeah, so yeah, we'll start with model 1 today. We'll just talk a bit about curves, and this in a topic such as curves, you'll find that many things will already be clear to all of us in various different degrees of our so to speak familiarity with the topic. So we'll of course ask a question: what is a curve? So this is the first thing. What is a curve? That is the very basic question of what is a curve. Of course, we understand it in a variety of ways, right? That even a line is a curve, right? Even a line is a curve. And say parabola, that's also a curve. Circle is also a curve, right? So for line, we can say that something y is equal to mx plus c, where m and c are constants. And then parabola, we have the simplest is y is equal to x squared. Then for circle, we have x squared plus y is equal to 1. So in general, what we'll say is we can formulate everything in terms of, say, this case y minus mx is equal to c. In this case, it's x squared plus y squared minus 1 is equal to 1. And here it is y minus x squared is equal to 0. In all these cases, we find that all of them have one generic structure which passes through all of them, right? So the generic structure is which unifies all of them. It is like f of is equal to c. So that is what it is. So c is a constant, and x and y are, of course, Cartesian coordinates. And f is some function. Again, f is a function. So mathematically, we would like to describe curve as a set of points. It's a set of points such that C will be some curve. In set form, it is xy is an element of R2 such that f of xy is equal to C. And I'll just add that even C is an element of R. So this is the base form of what we call as a curve. Right? And this is in planar. So this is a planar curve. And in, say, in 3D, we will have curve as a function, say f1 or say g of x, y, z is equal to c1, right? And these are all some level curves. In such that only those combination of x and y coordinates, x, y, z coordinates, which fulfills this relation, is what we call as a curve in 3D space, right? Now we want to build a more, say, mathematically rigorous definition. Let's build a more rigorous definition of what we call as a parametrized curve. So the idea is that what we have been discussing here, these level sets, they have a problem that we need to bind these quantities in order to get some, in order to determine the coefficient. I mean, in order to determine the, so to speak, the line at the curve, so to speak, right? However, we would want to have a curve in such a way that there should be some parameter which say if we are following this curve here, and say if it's a planar curve, then we all that we require is x and y coordinates. Then when we move along this surface, along this curve here, and from the definition of this, a curve is set of points such that what we would be doing is we would be just generating some points scattered here and there, just all those points which satisfy this, right? Of f of xy is equal to c. However, what we see, it's very what you call untenable to actually get a to determine the curve just because by brute force determining all those points which satisfy this relation. So we would like to have a more systematic way, that why don't we have, say, a starting point for this curve, and there should be something which allows us that as we vary that some variable, we will be tracing this curve. So it's like in his say we are given this point, and we know how to systematically move from here point by point, and then gradually constructing this curve. This is called a graph, or the graph of a curve. Uh, so in this case, what we call is that we are parametrizing this curve here, right? So it's like we start with some initial point here, and then gradually build along it in order to get something called as a parametrized curve. So now let's define what is a parametrized curve, right? So a parametrized curve in Rn is a map. The map is gamma vector. So all those vectors I would have an it will be just underlined, so to speak, right? So gamma vector alpha beta to Rn for some alpha and beta with minus infinity is less than or equal to alpha, which is less than beta, which is again less than or equal to infinity. So this is how we define a parametrized curve. Now let's try to understand the definition here. It says that a parametrized curve in Rn space, which is some very generic space, is a map from an open interval alpha beta to Rn for some alpha beta which is bounded on both sides by infinity. So we can even have curves of infinite length because we are just keeping it as free as possible, right? Without any putting any constraint on the open set or on the intervals, right? So in this case, alpha beta is an open interval which is such that t is an element of R, alpha is less than t, which is less than beta. So this curve, this parametrized curve, whose image is contained in a level curve, is called a parametrization of C. Of or sometimes even part of C, because right. So it's like when we trace this, I mean, it's maybe once we do some examples, this idea will become more clear. Is that, say, when we parameterize this, right, and when we as we keep on incrementing t, we will have every point in R1 one point at a time. We are just constructing it, And since we do it continuously, we'll have a continuous set of connection between all those points, which will eventually give us a curve or the graph of the curve. So that's the reason we call it that the image is, of course, the level curve C. And this particular thing is called the parametrization of this curve. Let's start with an example. I think then things will become more clear. Right. So say we have an, let's do an example. Say we have the parabola, which was y is equal to x squared. And let's build a parametrization for this curve. For parabola such that y vector t, and since we are dealing with planar curves, we'll have two components, gamma 1t and gamma 2t. So and this corresponds to the x coordinate and this is the y coordinate. And as we recall from our level set form of the form of the curve, what will have will have certain relation which binds both of these components, which is essentially y of gamma 2 t is equal to gamma 1 t whole squared. Now any relation which satisfies this condition, any value or any expression for which any expression for gamma 1 of t and gamma 2 of t which satisfies this relation is called a parametrization of C for the parabola. And here we have a problem. The problem is that let's start with some examples. Then I think you'll be easily able to understand where the problem lies. Say if we have gamma 1 of t is equal to say t, and gamma 2 of t is equal to, all that it has to do is satisfy this relation. So it means that gamma 2 has to be equal to gamma 1 square, which is t squared. Now at the same time, I can even have gamma 1 of t is equal to t by 2. And then gamma 2 of t is equal to, all that it has to do is take the square. So it's like t squared by 4. T squared again. So it will be gamma 4. So what we see is, the problem that we see here is non-uniqueness. So even though we had a parametrization of the level curve, in this case it's a parabola, we are unable to get a unique parametrization, because the thing is the choices are infinite, right? So what we would do is, we will want to have some unique parametrization. So the question is non-unique. So what is the unique parametrization? And of course, this question we'll answer it little later. Before that, let's explore some more examples, a few more examples. Let's consider circle. This will be answered later as we progress along. Let's look at an example of circle, right? So the equation of a circle is x squared plus y squared is equal to r squared, which is some real positive real number. So let's have R to be 1. So it's a unit radius circle, right? So your square plus y square is equal to 1. So let's construct some parameterization. Y vector is equal to gamma 1t and gamma 2t. So the condition which this has to follow is, as usual, there is x coordinate, there is the y coordinate. So we'll have is gamma 1t whole square plus gamma 2t whole square is equal to 1. We can have several examples, again, several, say, parameterization. Say we choose uh, gamma, I mean, before that, let's have gamma 2t is equal to plus minus over. Before that, let's just take the positive, say 1 minus gamma 1t squared. Now, the issue we see here is, let's say gamma 1t is equal to t. Then what we have is gamma 2 of t is equal to root over 1 minus t squared. Although it seems like a parameterization, but when we really plot, and as we vary, say, t from -1 to 1, of course, so t will be an interval, right? It is an interval. So it's say -1 to 1. As we increase, we'll see that we are only able to obtain the upper part with the points lying on the x-axis, not lying, I mean, not included in the curve, right? It's open set, right? So what we see is, using this parameterization, we're only able to obtain half of the curve. I mean, half of the circle. So this definitely means that there is some issue with the parameterization here. And of course, you would suggest that, okay, why cannot we have plus minus? But the issue, as we clearly say, is that it's no longer a function then. Because for the same value of gamma t, you have two values of gamma 2t, right? So say if we take both plus minus, then of course we cannot have both. So it does not satisfy the condition for a function, isn't it? So what we would require is, let's just clearly look at this expression, and of course this one, and we'll try to find something which is always valid. I mean, where we don't fall in such pitfalls, right? So one parameterization which is very useful here is that gamma 1 of t can be taken as cos t, and gamma 2 t is to be sin t. And when we square both these terms and add, of course, it's 1, right? So it means that parameterization is fine so far. Now the idea is, what should be the interval for t? So we can have t from 0 to 2 pi. So isn't it, in this case, the way we build is, we start from here at 0, we'll have 1 0 will be the coordinates, and gradually we build up and eventually end up just before it, because of course it's open on the right hand side of the interval. So which means that we are able to construct it. And even if, say, t happens to be, if the interval happens to extend to, say, from 0 to 4 pi, it's still valid. But the issue is, like, we are repeating things. So we would always want to have any interval in real number in R would suffice, provided the length of the interval is at least 2 pi. That is the minimum requirement, so that we can have a good enough parameterization for the circle, right? And after this, a major assumption that we'll be having, we have throughout this course, is that all parameterized curves will be assumed to be smooth. So the thing is that the smoothness requirement helps us to say not worry about the differentiability of the mappings, right? We can have infinite, uh, we can have all the orders of differentiation, and all of which will be continuous, right? Now let's talk about what is a tangent vector. So definition, what is a tangent vector? So if gamma vector is a parametrized curve, its first derivative gamma dot is called the tangent vector of gamma vector at the point gamma vector t. So this is how the definition goes, and I must just slightly digressing here. There is a difference between f and f of x, right? I mean, you must always keep in mind. In maths, there is a strict distinction between f and df by dx. F is a mapping, and f of x is the image of the mapping. And mind you, it's a very strong, I mean, it's a very strict, oftentimes we confuse between both, but f of x is more like a value. It's a value. So say when you do df by dx and then df of x by dx, this has both of them have different meanings. Like df by dx is actually we are finding the derivative of the mapping, and d of x by dx is not a valid operation in say when we actually do in rigorously in maths, because here we are trying to differentiate a value with respect to the quantity. So yeah, so there is where, so this distinction must be kept in mind, but oftentimes, as you'll see that we in practice we do not tend to follow the distinction here because we use them interchangeably. However, this distinction should always be kept in mind when we do all these operations in calculus, right? So we were talking about tangent vectors. So if say gamma vector is a parametrized curve, say we have a gamma vector which is a parametrized curve, and its first derivative gamma dot vector. So we have this gamma vector from here to here, right? So the derivative at any point. So this point will be, I'll just call it, of course, gamma from alpha is this here, and the mapping is gamma vector, and this point is gamma vector t. And this tangent here is gamma dot t. Right? So this is what we call as the tangent vector. And of course, yeah, everyone is aware of this very well. Right? And how do you understand what is a tangent? To understand a tangent, let us first, of course, on the same, let's make a similar curve here and take 2 points. This gamma t vector and this is gamma vector t plus delta t. And equivalently in the real plane, of course, alpha beta are not included. So alpha beta This we have t, and this we have t plus delta t. So this vector is this line joining both of them is a chord. Right? Now what we see is that the distance of this both the between these points is gamma vector t plus delta t minus gamma vector t, right? And divided by delta t gives us the rate of change, right, of the difference between the length divided by the distance in the time, isn't it? I mean, define with the change in the parameter t, not time exactly. So what we see is now if as delta t is tends to 0, then the length of chord also tends to 0. However, what we see is the direction of the chord becomes parallel to that of tangent to C, to the curve, like this is the curve C at the point. And from limits and continuity, limits and derivatives, what we had learned during our school years. So delta t tends to 0, and this entire expression here is as we gradually move towards the end. So the tangent will be, of course, the tangent at this point is given by like this. So as we bring this point gamma vector t plus delta t closer and closer to gamma t, we are actually approaching to the along. We are just falling in line with the tangential direction. So that is what. So we start. So essentially, tangent is a chord, right? Only when the distance between the 2 points on the curve with respect to the point where we are finding the tangent is just moving towards 0. That's how we define a tangent vector, right? And now this tangent vector would only be useful. So gamma t, it's only useful or only defined if d gamma vector by dt, which is essentially the same, is not equal to 0 vector. This is a very strong requirement, right? And we later learn that this is required for any curve to be called regular, and we only deal with regular curves when we in differential geometry. Now, just as a suppose what we call as in this Presley's book, he calls it proposition. So proposition are small definitions. From the larger picture, or part of a larger picture. So proposition is that if say gamma vector t is constant, so this implies that the image of the curve, so image of the curve is the actual representation in xy plane, is either the straight line or it's part of the straight line. And we can clearly even derive this from here. Say we have gamma vector t is equal to some constant vector a, right? When we integrate it, say we have d gamma, we can of course write this down as d gamma vector t multiply both sides by dt and then a vector dt. So this of course cancels out. So what we'll have is gamma vector t from say 0 to some t, even this goes from 0 to t. Then we have gamma of t minus gamma vector at 0 is equal to a is a constant. So a vector comes out, then we are integrating from dt from t 0 to 2. This will be a into t. So and this gamma of 0 we can just call it some b vector because it's essentially a constant. So gamma vector is equal to a vector t plus b vector. And b is a constant vector, of course, right? B is constant. It's a constant of integration, right? As we learned. So how it would actually look like in this is the origin of the coordinate system, and any point on this line here is given by gamma vector t, and then b is this is the vector b, some constant line, and a is just the direction along which the line goes, right? So a was the directions, so it's like this is the ta vector. And as we know from our vector addition that of course gamma t vector is equal to b vector plus ta vector, which is essentially this, right? This is what to show how it whether it's really true. We were able to show that if gamma t, and in this case we see that we clearly see that gamma dot t, when we differentiate with respect to t, then we are only left with a vector, which is essentially our initial proposition. So I believe, yeah, and maybe one more thing, and then we'll maybe wind up for today, right? Now let's what we call as the arc length. So in arc length, what we say is that if v vector is some say v1, v2 till vn, it's a vector, right? Say it's a vector in Rn space. Its Euclidean norm, its length is root over v1 squared plus v2 squared plus vn squared. And this is also called as the Euclidean norm, or even L2 norm. We look at function analysis, right? And say if u vector is another vector in Rn space, then u norm of u minus v is essentially the length of the line segment connecting the points u vector and v vector, and of course in Rn. Now, as we recall from some time back, we are talking about code and all, right? So we have this say curve and some 2 points, and we just join both of them. There's there's gamma vector t, sorry, and there's gamma vector t plus delta t, And of course, the line connecting both of them is the length, right? Length of that chord. However, since delta t is small, of course, we are taking alpha, beta, and then this t, and this is t plus delta t. And this delta t is very small. So it's epsilon, which is just greater than 0. Since delta t is very 0, then what we know from here is that the distance currently between these 2 points is, or the distance of the line connecting these 2 points is, right? Now, we know that gamma vector t plus delta t minus gamma vector t by t by delta t was approximately equal to when delta t tends to 0. So which means that we can write this expression as norm of gamma vector t and delta t. And likewise, if we do for all those segments, which every two consecutive segments on this 2 points on this curve, we will eventually end up with, say, something like we start with I is equal to 0 here, and I is equal to n. Let these be the points at which we are interrogating, right? So the total, let's this see, the total length of C, of course, approximate, since we are not actually following the curve here, is equal to the summation of gamma vector at ti into delta t from I is equal to 0 to n minus 1. And where this consecutive distance is delta t. But say when n tends to infinity, like we are taking a lot of, I mean, an enormous amount of points, like infinitely many points on this line, and then we are trying to find the length. Then the total length what we have is, then we approach the total length becomes from it just like we know from the Riemannian sum, right? I think we had learned in our school years that we can move from summation to integral, right? So as when t delta n tends to infinity, then we have delta t tending to 0. So eventually this summation will end into an integral. So it will from alpha to beta, and then of course we to have gamma vector of t into dt. And this is what our total length actually is. And this is also called as the arc length of the curve. Right. So a few more definitions, and then I'll just give a very basic introduction to Mathematica today, just so that it will be somewhat encouraging. Definition of an arc length, right? So the arc length of a curve gamma vector starting at the point gamma vector t naught is the function s of t, which is given by s of t is equal to t naught to t and gamma dot u norm of this into du. And as we see, if or thus what we see is ST naught is equal to 0 because we are starting from the same point. We are not moving any further from the same point, and S of t is greater than 0 or S of t is less than 0 depending on whether t is greater than t naught or t is less than t naught. So that is what arc length here we talk about, right? One example, which is of course it will help us in understanding. So let me draw a circle of unit radius. Radius is 1. We start from here and we proceed this way, and we learned from the arc length parametrization that we have, of the parametrized curve of the circle to be gamma of vector t is equal to cosine of t, comma, sine of t. This is 0 and xy coordinates. So, and we also knew that t will vary from 0 to 2 pi with 2 pi not included. Now what we do is, now let's just analytically find arc length, the arc length of this circle. And I'll call it total arc length, which means that I start from here and come back to there, covering the entire circle. So what we'll have is S of, I'll call it t is equal to 2 pi, and we start with 0 and 2 pi. And before that, we need to determine gamma dot vector. And then we'll differentiate terms individually. So it will be the derivative of cosine t with respect to t is minus sine of t, and the sine of t with respect to t is cosine of t. And the norm of this is equal to, as we learned from the Euclidean norm here, v1 square, this is square sum, square root of the squared sum is equal to minus sine whole squared is nothing but just sine squared t. Likewise, cos t squared is cosine squared t. And you know very well that sine square plus cos square is equal to 1. So this becomes 1. So S is equal to t is equal to 2 pi. So we'll have, the definition is gamma t dt. And we are able to determine the expression for gamma t to be 0 to 2 pi into 1 into dt. And this becomes 2 pi, right? Fine. So this is the total arc length. We would like to verify, right? So let's verify. So this circle has unit radius. And we know the circumference of a circle of radius r is equal to 2 pi r. And when r is equal to 1, then you already have the answer. Circumference is equal to 2 pi into 1 is 2 pi. You are able to see that both the answers, the results are the same, because essentially circumference is the total arc length of the circle, right? So yeah, I think I'll stop this theory part for here today, and I'd also be sharing the notes. So if it is really, if you really find useful to say revise, then I think this is where you have to. I mean, I believe this will be really helpful. So what I'll do is I'll just share the Mathematica file that I had been working on.